So in number 66, at a certain factory, 300-kilogram crates are dropped vertically from a packing machine onto a conveyor belt moving at 1.2 meters per second towards the left in our picture. A motor maintains the belt's constant speed. The coefficient of kinetic friction between the belt and each crate is 0.4. After a short time, slipping between the belt and the crate ceases, and the crate then moves along with the belt. For the period of time during which the crate is being brought up to speed relative to the belt, calculate for a coordinate system at rest relative to the factory the kinetic energy supplied to the crate. So, a couple of quick things first of all. We've got this going with a velocity of 1.2. Friction always acts against the slide or potential slide. In this case, it's interesting. The force of friction is going to be actually acting this direction, because when it first hits the belt, the tendency is for it to actually, the belt's moving underneath it this way, the crate is sliding this way relative to the belt. Friction's going to be acting against that slide. Also, please remember, kinetic friction, when something's sliding against something else, that's a non-conservative force, which means it's actually going to be generating some heat as it goes. So solving this one, I'm going to use 9.8 for gravity. So this is the force normal. Is going to be this. You could also use 3,000, but I get the force of kinetic friction is going to be 1180. Now, that 100 or 1180 newtons does not immediately get it up to speed. It actually slowly gets it going there. So first of all, let's say answer A. The kinetic energy supplied to the crate. Eventually, the crate's going to be moving at 1.2 meters per second. So how much kinetic energy is the crate going to gain? The answer is 216. We've already solved B, the frictional force acting on the crate, about 1180. But C, the energy supplied by the motor, and this is where the tricky part of this one comes in. Why? It's actually going to slide along the belt for a little ways until it finally gets up to this final velocity. How far is it going to do? Well, we can actually solve this. We can take the force of friction, that's our force acting on it, mass of the crate's 300. We'll discover that the crate's going to gain speed at 3.92 meters per second squared. That's its acceleration. How far is it going to slide during that time? Well, eventually it's going to get up to 1.2 meters per second. Starts out at 0. The acceleration is this number we just got right here, and we're trying to solve for delta x. And we'll discover that it's going to slide along the belt that far before it gets up to speed. So how much work is done by the force of friction, kinetic friction, during this time? Well, we know the force of friction is this, and the displacement is going to be this from our previous answer. Interestingly enough, that's the same number as the kinetic energy gain. So how much total work was done by the motor? Well, the crate's going to gain 216 joules due to the kinetic energy. It also generates 260 joules of heat because of the force of friction as this thing's sliding along here. That's generating E dis, or heat. Total amount of work done by the motor is this. Question D, explain why your answers to A and C differ. The answer, because the motor is not only getting it up, increasing its kinetic energy, but it's also doing work against friction, and it's generating heat. And that's why we end up with a much larger, or double, the energy generated by the motor. That was a little tricky. Hopefully it made sense to you.